Okay, so welcome everybody, and yeah, congratulations to everybody who's hung on to the almost the very end of it. I know everybody else is really busy with their projects and everything, and of course you'll all be watching those videos online later, right? But so we still actually have a lot of interesting things to go through, and yeah, by all means ask questions. So today we'll go through things at a slightly accelerated speed. That has a lot to do with the fact that in the previous lectures, we didn't go through things with an accelerated pace, and I still want you to learn about a couple of, I think, useful techniques, and so we'll just go through it a bit more rapidly, and slides will be available online. Okay, so we'll do exponential families, and then EM and clustering, and a few other things, and maybe hidden Markov models, all in one lecture. Don't worry, it can be done. So, exponential families, why on earth am I doing this crazy stuff here? Well, basically, there's this big zoo of, distributions that you may have heard of, and the question is, is there any rhyme and reason between them? Can I actually capture all of them in one mechanism? And it turns out you can, and that makes the math for them a lot easier. And okay, so this is the pretty picture. Now here comes the pretty math. So basically, they're all members of what's called an exponential family, and they are given by p of x parameterized by theta, given by e to some inner product between phi of x and theta minus g of theta. Okay? So does somebody have an idea what this g function does? It normalizes, yes. It makes sure that the entire thing integrates out to 1, and so we can actually derive the equation for g, and that's nothing else than, well, we need to make sure that exp of phi of x dot theta minus g of theta dx equals 1. And if we do this, then we get that basically e to the g of theta is this integral. And then taking a log of that, we get exactly the expression here. The main difference being that on the slides I have a sum and here I have an integral, but yeah, that's just how I am treating various domains. Now, one of the really cool things about this g function is that if I compute the derivative, I can show that this amounts to the expected value of phi of x, where x is drawn from that very distribution up here, and that the second derivative gives me the variance. This is super cool because now, if I've computed g, I pretty much have everything that I need to know about the function, about my distribution. All I need to do is just compute derivatives. You can also use this to sometimes identify the distribution by just computing, let's say, first, second, maybe third order derivatives, and then match up the moments to these parameters. This is, for instance, what spectral methods often do. One really useful thing is, if this is the variance, we know that the variance can never be negative. So we know that all the eigenvalues of this matrix are greater or equal than 0. So therefore, we know that G is convex. This is super useful because we can then bring to bear all the tools from convex optimization that we did before in the class. So there's a reason why we went through all this convex optimization mess, because now we are reaping the benefits from it. Okay. Computing mean and variance, well, it's just what happens here on this slide. I'm going to spare you walking you through the variance part, but for the mean, basically all we do is we just apply the chain rule. So d theta of g of theta is d theta of the log of this integral. Now the log, we just divide by this term, and then we pull the derivative into the integral. And so we get, phi of x e to the phi of x of theta. That's just how, well, exponential functions are derived. And then, well, massaging the math a little bit, we can recognize that this is just phi of x times this term here, which just so happens to be p of x parameterized by theta, so it's the expectation. And a little bit more algebra, it's not terribly deep, but a bit more tedious, gives you the second order moment. You could go on for higher order moments. Any questions so far? One case why this is extremely useful is because sometimes it's going to be really, really hard to compute g of theta. But it may be easy to draw from that distribution by, let's say, a Metropolis Hastings sampler. Don't worry if you don't know what it is, look it up on Wikipedia. There's actually a really nice summary for Metropolis Hastings and Markov chain Monte Carlo sampling. We'll touch it a little bit, or even better, take 10702 or something like that, or graphical models. I think Eric Singh is teaching it next semester. Bottom line being, in some cases, computing g or its derivative can be really hard, but by knowing that this corresponds to the expected value, as long as I can draw from the distribution, I can compute the derivative without even having access to the function. This is kind of weird, right? It's easier to compute the derivative than actually get that function itself, but the derivative is all that we need for optimization, so we can optimize and infer parameters without ever having access to g. In some cases, we can make our life algebraically easier by just having access to g and algebraically computing derivatives, and then we immediately know, what the mean and variance are. Okay, so let me give you a few examples. Binomial distribution is an example of that. Discrete, a Gaussian, Poisson, Dirichlet, beta, gamma, Wishart, all the ones that you saw before, and we'll go through them in some more detail. Let's start with something simple. Let's take a binomial distribution. So I'm picking phi of x is x, and in this case, I get that p of x is 1 over 1 plus e to the theta if x equals 0, and e to the theta divided by 1 plus e to the theta if x equals 1. So you can see that very easily. So if phi of x equals x, and furthermore x is in the set 0 and 1, then, well, g of theta is the log of e to the 0 times theta, so e to the 0, which is 1, plus e to the theta, right? So it's log of 1 plus e to the theta. Has somebody seen an equation that looked a little bit like this before? When did we do this before in class? Yes, somebody's whispering the right thing. Louder. Hey, come on, wake up, guys. I know it's Monday morning. When did we see this before? Hint, classification. Logistic regression, exactly. So there, we saw this thing, right? We had p of y given x and f was something of the form 1 over 1 plus e to the minus y times f of x. And the y's were 1s and minus 1s. By some slight manipulation of the algebra, by going from y's being 1 and minus 1s, going into 0s and 1s, you can actually get it from here. Basically, what we did there is that this quantity was being governed by this f of x. So in other words, we made the probability itself a function, well, the natural parameter itself a function, and we optimized over it. And that trick you can use many times over. So this way, a conditional binary model is classification, right? Because if I conditionally want to decide between apples and oranges, that's a classifier into apples and oranges. A conditional normal model, and the normal distribution is also a member of the exponential family, well, what would that be? If conditioned on x, I estimate some real valued number. What am I doing there? Guys? Regression, exactly, perfect. So I'm just building a regression estimator. As a matter of fact, not only can I, as it turns out, estimate the mean, but I could estimate the mean and the variance. And this is then called heteroskedastic regression. Whoever came up with this word, well, okay, liked to spell complicated words, but it's basically a complicated way of saying, well, I'm estimating mean and variance. I can also do Poisson distributions. And if you rewrite them, and I'll do that on the next slide, you can basically come up with a conditional Poisson model. Now, Poisson regression isn't quite so popular usually in machine learning, and I'm not quite sure why, because quite often you do have count data. So often people approximate that by a Gaussian, which is quite horrible. But this would be a much better model for modeling distributions of accounts. An example of where Poisson distributions come from. So to give the example of right now we have snowflakes, and you can basically look at we'll get a certain amount of snow per square foot over a given time. Now you can ask how many snowflakes are we going to get in the, and let's assume that the amount of snow that we're getting is maybe even stationary. So then you can ask, how many snowflakes am I expected to get in the first half of the time and the second half? And I can make those intervals smaller and smaller. And the sum over the counts over those intervals is going to be, the expected value of that is going to be the same. But now what we get is in those smaller and smaller intervals, we'll get, again, a distribution over events. And the overall distribution that you get, if you ask, how many snowflakes will I see, let's say over 10 minutes, is going to be Poisson. So it's just, saying that the number of snowflakes I get in 10 minutes is the aggregate over the snowflake events for each of those infinitesimal intervals. A rather morbid example of where the Poisson distribution also applied. So Prussians, more specifically the Prussian army, was very well organized. So they kept statistics on everything. For instance, the number of soldiers who died from a horse hitting them on their head. Now this turns out to be a completely random event. Horses do that for no reason. And it turned out that if you look at the distribution over soldiers dying from being hit on the head by horses, is Poisson distributed over a few decades. Okay, so I suppose that's also because there was no technological advance in keeping horses from hitting soldiers on their head. Okay, so here's the math for it. So I can write the Poisson distribution that we saw before as 1 over x factorial e to the x theta minus e to the theta. And just to briefly explain what we have here, these are the count distributions. So it actually shouldn't be a line technically, because you just have discrete numbers of different counts. What you see is actually, for the rates getting larger and larger, this looks more like a Gaussian, and that's not entirely coincidental, because basically the Gaussian and the Poisson are just limit cases. If you take a binomial distribution and you increase the number of events, in one case the limit distribution is just fixed mean letting the number of observations go to infinity. In the other case is I have a certain expected value, and I partition the number of events such that each individual event probability goes to 0, and that gives me the Poisson. Basically, Poisson approximates the outwards tail. All right, so if this is my binomial distribution, then Poisson focuses on this part here, and Gauss focuses on this part. That's very roughly what's going on. So the probability distribution here is 1 over x factorial e to the x theta minus e to the theta. So remember, the sufficient statistics are exactly the same. I haven't exactly explained yet what sufficient statistics are, but basically they are a pre-processing of my data in such a way that if I just use the process data, I don't lose any information. That's what a sufficient statistic is. You can write it in terms of conditional independence if you want. And one of the nice things about the Poisson is you can actually solve this integral 1 over x factorial e to the x theta sum over all the x's. This can be solved. And in particular, it gives me this term here. Then I can compute the expectation and the variance. So what we can here see is that the rate is the same thing as the variance of that distribution. It's kind of a strange distribution that has this property. Yep. Yeah. E to the minus e to the theta. Well, wait, where?
The 1 over x factorial.
Yeah, yes. It was correct here, and it got wrong there. I'm sorry. Yeah. You're absolutely right. And on the previous slide, it's correct. So, please correct that. Yeah, they got flipped. I'm sorry about that. Thanks. Okay. Somebody's paying attention here. It's very good. You can get crazy distributions like the beta. And actually, as it turns out, the beta is what's called a conjugate to the binomial. And I'll explain in a moment what this is. And so just with two parameters, I mean, you can get this very rich zoo of different distributions. So if I have a distribution in a unit interval, probably betas are quite useful. One of the reasons why I'm going through this is because these are distributions for which statistical inference afterwards is really easy. And in many cases, you won't have a particularly good idea of the distribution anyway, so you might as well pick a model that makes the implementation easy. These are Dirichlet distributions over 3 possible events. So that's basically a generalization of the beta. So the interesting thing is that those events have to sum up to 1, so that's why I'm sitting on a simplex here. And so you could think of this as a distribution over distributions, right? Because you basically have numbers that have to sum up to 1, in this case 3 numbers. So it's a distribution over distributions with 3 different outcomes. And that notion of a distribution over distributions is something that, in the context of Dirichlet processes, people extend quite a bit further to distributions over infinite numbers of outcomes and countable ones and so on. So this is a very interesting point of departure, how you can generalize this. But what matters for us here is simply, well, we have a very simple exponential parameterization. It's just e to some inner product between phi of x and theta, and that normalization, and then, mean and variance can be easily obtained. Any questions so far? I know we're going fast through this stuff, but I just want to get it covered. Okay. Inference.
Are there any distributions that we know of that don't fit into the exponential family?
That's a brilliant question. So the answer is yes and no. Okay. So first of all, there's a very nice result showing that for large class of Bregman divergences, they can be written in terms of an exponential family in a product and so on. So there's very nice work that came out of U Texas a couple of years ago along those lines. The short answer, however, is no. Basically, there are only a small number of distributions for which you can compute this normalization in a meaningful way, right? However, what you could do is you could just say, well, let phi of x be a member, of some, of some feature space, maybe for kernels, right? And then you have e to the phi of x dot theta, and this actually does cover a ridiculously large class of distributions. The reason why I said, well, actually the answer is probably no, is because in this case, computing g of theta is essentially hopeless. Because you'd have to solve an infinite dimensional integral over the entire domain, and you usually cannot do this. So what you then do in practice is you make approximations and simplifications that allow you to approximate and estimate the integral. And in doing so, the class of distributions for which you can actually use exponential families tools is reasonably limited to, for instance, what people call undirected graphical models. So there, a lot of the clique potentials can actually efficiently be written in terms of inner products, and some directed graphical models. So for instance, we'll get some of them in the context of hidden Markov models and so on. But this is a very good question that you're asking. It's actually very much at the boundary of what people currently think about and do research on. And essentially, the computational issues are probably the most pertinent ones. Yeah, so thanks for asking this question. It's good.
So to pile on to the answer, there's two things to think about here, right? One is any individual distribution, and the other is a set of distributions, right? And so an exponential family of distributions is a set, like the set of all normal distributions. Pretty much any distribution can be represented as a member of some set that's an exponential family. Right. Pretty much any distribution can be represented as a member of a set that's some exponential family, but it could be that a particular set of distributions does not form an exponential family, right? So I don't know, like if you have like all normal distributions plus all Poisson distributions, there's no nice exponential family that gives you that set.
So there, you already run into trouble because the domains are different. So if you had the same domain, then again, you may or may not be able to cover them. That's it. If I have the same domain, then, and each of them individually is a member of an exponential family, then in combination they also are. You can see this very easily. Let's say I have exponential family with phi of x as sufficient statistic and domain x. And I have another one with psi of x a sufficient statistic and also domain x, right? Then I can define some phi tilde to be just a stacked up version of phi of x and psi of x. And I will correspondingly have a theta tilde, right? And now, of course, p of x parameterized by theta tilde is exp to phi of x, let's say theta phi, plus psi of x, theta psi, minus, and now unfortunately normalization needs to take both of those terms into account. So therefore, if I have two exponential families, pasting them together and creating the union of them is fairly straightforward. However, in general, solving this integral will make my life so miserable that I won't be doing it.
And also it will get you more than just the union.
Yes.
Right? So the union won't be an exponential family, but you can complete it to get an exponential family.
So a simple example would be take univariate Gaussians in x and let's say y. Then the union of univariate Gaussians in x and y, well, that's just, two separate families. But by this construction here, I can then have anything in between that's also an exponential family. So that's a very important point. Yes. Any other questions? Okay. Let's see how we can actually set those parameters. By the way, what I entirely swept under the rug is a domain normalization. So for instance, for the Poisson, we had 1 over x factorial, but that's about the only pathological example that I currently know. For all the other cases, we have standard counting measures, or we have the Lebesgue measure as the underlying domain measure. So basically, we need a measurable space. So the negative log likelihood, if I draw the observations ID, it's just, well, minus log p of x parameterized by theta. It's the log of the product I going from 1 to n, p of xi given theta, which just by definition is g of theta minus phi of xi dot theta. Okay. So now if I want to maximize this, I need to take derivatives and set it to 0. Right? So now we have, okay, n changes into m, but that's, okay, this is n ignore that other part here. And because we know that g of theta, the derivative of that is the expected value of phi of x, so that's what we proved before, minus, and then here, okay, m changes into n, sorry, 1 over n, sum over I going from 1 to n phi of xi. This needs to vanish. So if you squint really hard at this and ignore the typos, you'll see that we basically get the condition that the expected value has to match the empirical average. That's our optimality condition, which now, for a Gaussian, for instance, tells us why we set, the mean and the variance to be exactly the empirical mean and the empirical variance. Because that's just what you get, from plain algebra. Right? So this is actually kind of nice, but it obviously raises an important question. When you're doing this estimation, these numbers, these quantities here are noisy. So you shouldn't be trusting them quite that much literally. And you can actually derive exponential families by saying, well, I want to have distributions that match my empirical moments and that have high entropy. So you can derive this entire form that I showed you before just from a maximum entropy moment matching point of view, and you get exactly the same equations. It's just a dual. Now, if you say, well, I shouldn't be matching them exactly, you actually get priors out of this. But that would be beyond 701. So let's go through a simple example. Observations are 0, 1. Sufficiency is phi of x is x. Log partition is log of 1 plus e to the theta. And so solving the inference problem, d theta of g of theta, is this quantity here. It's 1 over 1 plus e to the minus theta. That's the number of 1s divided by the total number of observations. And so what we get is exactly what you would have done already anyway, as in this is probably something every 10-year-old can tell you. Count the number of times the coin comes up heads divided by the total counts. Okay. This is the most complicated way how to ever get to this conclusion. This is a slightly less trivial but still quite straightforward conclusion if you have now k different outcomes. So there, the log partition function is just the log of e to the theta i's. This is sometimes also known as a softmax if you do neural networks. And then the probabilities here are set by counts divided by total counts. For Poisson, same game again. So the only non-trivial thing, as I promised you, was this measure on the domain, which actually doesn't really factor into the entire inference approach because it doesn't depend on theta, so the log derivative of that goes away. And then we have, d theta of g of theta, that's e to the theta. And that needs to match, sum of xi's, so therefore theta is the log of this. And then you just plug terms in. You're done. So basically, all you do is you just take the average rate and make that the natural parameter. Take the log of the average rate, and that's your natural parameter. It's very simple. Okay, any questions so far? I know we're going through this really fast, but we have another 40 slides to go. Okay, good. Conjugate priors. Now this is conceptually probably something you may or may not have seen yet. So the issue is that usually we have, not enough data. So then the question is, can we use priors to, improve our estimates? So of course, by using Bayes' rule, you could have something like p of x parameterized by theta times p of theta, and that gives us a posterior. So far, there should not be any surprising at all. Now, the thing is, if you do this, then often your posterior has a different functional form from your prior, and so inference gets hard, and you can't use your maximum likelihood inference codes anymore that somebody else already wrote. So is there something that we can salvage a lot of code and also have nice theoretical properties? And that's exactly what conjugate priors do. So by construction, conjugate priors are such that the prior and the posterior look the same. They are of the same functional form. That's how they're defined. Now, one way to achieve this is by treating the prior just like fake data. Right? Because if the prior behaves like fake data, then adding real data to fake data will make my posterior also look like, well, a distribution given, the real and the fake data now combined. So more specifically, let's say I make my P of theta be proportional to P of x fake given theta. And so therefore, by Bayes' rule, I get P of theta given x is P of x given theta times P of x fake given theta. And that's, of course, just P of the union between x and x fake given theta. Question: why is this a proportional sign here? Why is that not an equality? Exactly, because this is just a likelihood. This is normalized in x given theta, but we want to normalize it in theta for those parameters, right? That's actually not always possible, but it turns out that for exponential families you can usually get away with it. So this is a little bit of a leap of faith to do this. The good thing is that our, algebraic expressions look very similar to what we had before. So remember, P of x given theta is e to the, this is my observations. This is m times the sufficient statistic. And now what I'm simply doing is I'm calling this green bit m naught, that's like the equivalent counts, times mu naught, that's like a mean. And now in the end I need to add this normalization here, which just makes sure that everything integrates out to 1. Now as a function of theta, not as a function of x anymore. Okay. So let me give you some examples. Let's say I have, a binary. I have two outcomes. Then, mu naught, a good choice would be 1/2 and 1/2. Right? That basically just means I have no idea whether I'm going to see, heads or tails. And so a good outcome would be 1/2, 1/2. What would be a good outcome in terms of a prior for Russian roulette? So, those guns have, 6 chambers. You put, I guess everybody knows what Russian roulette is here. Gun with 6 chambers, you put the bullet into one, you spin it. What's a good prior for Russian roulette? One 6 and 5 6. Okay. So if let's say I go and play, let's say we toss coins, and you know that I'm trustworthy, then probably you should pick a reasonably large M0 here. That basic amount tells me how much, encodes how much you trust you. So for instance, if I play a game of coins with Joff, because I know he's very trustworthy, I'll probably give him M0 equals 100. Now let's say I go somewhere downtown and there's some shady guy on the corner and he says, well, I want to play a game. I'll probably give him an M0 of 0.1, right? You probably shouldn't pick a negative one because otherwise the integrals don't work out. But you probably wouldn't trust the shady guy downtown very much. But Joff is very trustworthy. However, if he keeps on cheating me, at some point I will, wisen up to that because, I picked m0 equals 100. So it will probably take a couple of 100 games before I find out, hey, I'm getting ripped off. Right? So this is essentially what you're encoding with your prior. So this is the algebra. Now, one interesting thing is that actually this entire expression here looks like an exponential family, right? So this P of theta, right? So here we have an inner product between theta and something, And then we have an inner product between, a number and some other number. So I can actually have a phi of theta to be theta and minus g of theta. And lo and behold, this just so happens to be now another member of an exponential family, but a slightly larger one. So what we've just shown with this simple modification is that conjugate priors themselves are members of an exponential family. So of course what you could now do is you could define a conjugate on top of the conjugate, and you could keep on doing this. The problem is that the integrals get really nasty, so nobody wants that. However, sometimes this is quite useful, especially if you need to compute derivatives. We know that, see, this is the normalization here. This plays the same role as our log partition function g of theta, such that if you take derivatives with respect to those terms, you get exactly the expectations out of it. So you can design very efficient algorithms by using that. And you can shortcut a lot of derivations. So sometimes in papers you would see things like, and we use a beta binomial or Dirichlet multinomial or gamma Poisson or Gauss-Wishart Gauss. And what they basically say is we use a conjugate prior and likelihood term. And then there's some paragraph of obscure things about some citation of a paper that's about probably 60, 70 years old, where they argue away derivatives. And almost invariably, they make use of the fact that those derivatives and that everything is nicely conjugate and how expectations look like. And the good thing is you can actually look those things up in Wikipedia. So some very nice people have worked out exactly what the terms are. Now, what we therefore have is the derivative of the log partition function of the conjugate is now just the expected value of our natural parameter and the expected value of the log partition function. That came from this choice here. After all, this is just the expectation of that. Okay? Now let's actually put that in practice. So for conjugate priors, let's say we have some means. Then what happens is that our averages, right, we now add something to them. So rather than just observing n real guys, we observe n real ones plus m fake ones. So I need to divide by that. And now I have to add a fake mean to it. And this is how much I counted. So I said Joff gets 100, the shady guy in the corner gets 0.1. And then, as a matter of fact, mu naught, so let's say it's even outcomes, as we already saw with the Russian roulette, right? It doesn't have to be evenly balanced. It can be something else that encodes what you expect to see. So let's actually do that for Gaussians. So for Gaussians, we basically have, means and variance given by, x and x squared. These are exactly our sufficient statistics. So, and you can work out means and variance from that. And then, these would be your standard maximum likelihood estimates. We've all done something like this before, right? We've just taken an average, and then we look at the sum over the average of the squares minus the square of the average, and that gives us the variance. And if we wanted to do a maximum posteriori estimate, we'd simply, and let's say our conjugate is something where we have zero mean and unit variance, then, we just take the average, but we divide by something that's a little bit larger than the number of counts. And for the variance, now I do the same thing. I add a little bit of the unit variance to it, so n naught over n plus n naught, and I subtract my mu hat from it. So this is now a smooth estimate, which will ensure that, for instance, my variance will never diverge. Because I just did this and decided 1 would be a good value for my prior on what the variance is. So I basically assumed that my prior guess is that I have data drawn from a distribution with zero mean and unit variance. Now, almost certainly for any specific problem that you're going to solve, this is wrong. You'll know more about your problem than it's 0 and 1. Let's say, for instance, I go and measure the voltage on a power outlet, right? I might have a pretty good idea that the voltage should be around 110 volts. And maybe I looked at my voltmeter before, and it says something like accuracy 5 volts. So then I would have, sigma squared to be 25 volts. Well, I would have basically this term here to be 25 volts squared. And I would have this not being that number, but I would basically take that sum plus, n naught times 110 volts. And this will give me my estimate for, trying to figure out what the right voltage is. And of course, if I measure enough, then my prior will be completely overwhelmed by the evidence, which it should. And before that, it's just quite straightforward. Let's go through this for counts. Let's say I have x is in the set 1, 2, and 3. And let's say I pick my mu naught to be maybe 1/2, 1/3, and 1/6. And I pick n naught to be maybe 6, just to make the math look nice. Or I could make it, let's make it 12, otherwise it's too trivial. And then I get some counts. Maybe I see the ones, 7 times. And I see the 2s maybe, 3 times. And I see the 3s maybe 6 times. Of course, now it doesn't work out. Let's say we see it 5 times, right? So then that means we have total counts of 15. So what I'll get is, for the probability of seeing a 1, we have 7 times, 7 plus. Now here we have 1/2 times 12, so 7 plus 6, divided by 15 plus 12. And then for the second probability, we have, 3 plus, 1/3 of 12, well, that's 4, divided by 27. And for the third term, we have 5 plus 2, divided by 27. And then you can work out this and get a probability estimate after having observed 1s, 2s, and 3s this number of times and having used this prior. You've almost certainly used this before. Have you ever used Laplace smoothing? Who has used Laplace smoothing before? Okay. Who's worked with documents before where you used word counts and you took logs of word counts? Nobody else has taken word counts. Wow. So, but you should have, because you had some text data sets, right? So what you probably would have noticed then is occasionally when you take logs of word counts where the word count is 0, then of course the log diverges, so everything's really bad. And then you may have been tempted to fix things by just adding 1 to all the counts and everything was good again. And then you were surprised that not only did this fix your problem, actually everything got better. And that's because you're effectively using a conjugate prior against the uniform distribution where all the words are equally likely to occur, and you're basically performing a map estimate. So what you did was something super sophisticated, even though you didn't realize it. This is called Laplace smoothing. So if you had ever done this, you would have already done this complicated thing just in a special case. Now, a really useful thing about conjugate priors is that they let you collapse out distributions. So about 10 years ago, you could have written probably about half a dozen papers on a collapsed something method for something. And then a couple of years later, it would have been a collapsed variational something for something. Okay. You can probably still occasionally do that, but it's not quite so spectacular nowadays anymore. But it's still an extremely useful technique in practice. So if you think about it, our conjugate priors, well, they're just P of theta is proportional to P of x fake given theta. So if we want to compute, for prediction, we want to get, P of little x, which is where we want to predict, given capital X. So trusting our model, well, what you have is, you have to solve the integral P of x parameterized by theta times P of theta given all the data that I'm observing, d theta. Right. That's just, that's basically what we want to predict. That's our posterior. So now writing this out is basically proportional to P of x given theta times P of capital X given theta times P of x fake given theta, d theta, which is that integral of real data union with fake data union with one extra data point, d theta. And that just so happens to be something that we already computed before, because that's the normalization for the conjugate prior. That's this h function. This guy here. Just with, slightly more complicated arguments squeezed in here. So in other words, somebody has almost certainly already done the work for you, which is good. And then you just look up that expression, and you then know what P of little x given capital X is. For Dirichlet multinomial, this turns out to be an amazingly simple expression. Namely, you get exactly your maximum posterior estimates back. Those guys here. You can look at it in detail because we already did this here. Now let me give you a list of those pairs. You don't need to remember them, and you almost certainly may not be able to even read this, but you can look it up on the slides. So what happens is that for the binomial, the conjugate is the beta. Multinomial, so that's basically k different outcomes, is the Dirichlet. For the Poisson, well, it's gamma, and for the Gauss, it's Gauss-Wishart, and yeah, this is obviously not a no, but it's an n0, so it's basically integers greater or equal than 0, and that's that. Let me show you, based on an example, what happens. So if I have an honest dice, the maximum likelihood estimate tends to be rather on the paranoid side, right? And map is actually pretty good. So this is as I get more observations, you can see it, smoothes fairly well. Maybe I should have smoothed even further. On the other hand, if I have a tainted dice, and there you can clearly see that not all the probabilities are equal, the map estimate initially doesn't really detect anything at all there. It starts picking up things here. I think this was 12, 24, 60, 120 observations. But it takes quite a while until it actually realizes that something very fishy is going on here. So this is the downside of using a prior. You become less sensitive to things that are different from what you expect them to be. But I suppose it's a little bit like in real life. I mean, you can be super paranoid and then you won't get anything done. Or you can be completely oblivious and then you might not actually notice when something strange happens. So what I hope to have showed you so far is maximum likelihood estimate, maximum likelihood inference is just moment matching. So you basically just pick your parameters to be exactly the same thing as your moments. And if you have a conjugate prior, it just means that you add some fake data to your real data and you do joint inference. Okay. Any questions so far? I know this was now a crazily large amount of stuff that we went through in a very short time. think 30 slides in 60 minutes is quite tough. Any questions? Okay. So here's a bonus slide for you not to steer over too much right now, but you can look at it later at home. This is, so last week Geoff did deseparation and basically conditional independence. And this is a purely algorithmic way of asking whether random variables are dependent on each other. And in a way, we already did a whole bunch of those things, right? So basically, those pictures ask, so shaded means observed, and the arrows mean, you know, the arrows of your directed graphical model. And so what you can see immediately is you get the thing of, you know, explaining away. So if you have an observed child of two independent parents, then by observing the child, the parents become dependent of each other. Likewise here, if I observe the parent of two children, then, well, basically these children become independent of each other. However, if I don't observe, then, you know, they are clearly dependent on each other. Whereas here, if I don't observe the common child, the parents remain independent. And these are just essentially corollaries of that. But, yeah.
In the last case, if you have three parents and if you observe one of the parents, will the extent be independent?
If you have three parents here.
And you observe one of the parents.
Well, I mean, in this case, if I observe a parent, nothing bad happens. Because I have several parents of one child. If I had a parent of two children, then they would become dependent, yes. So what you do is actually you use this algorithm and you run what's called baseball. Yes. There's a paper called baseball. A rational pastime by, I think, Schachter. And that has this algorithm in it. But basically, all you need to remember is this one picture. I don't want to go into too much detail here, but this is just a very useful visual aid if you ever have a directed graphical model and you're not quite sure what's dependent on what, given what we observe. You basically run this algorithm, and if you can reach one vertex from another in this manner, then you know they are dependent.
The summary is if they're dependent if there exists an active path. And so if you're worried about other nodes in the graphical model, well, you just need to check, you know, whatever you think the active path is, you need to check that every node along that path is active according to these rules.
Okay. So now we come to the last part, namely clustering. So I told you we were going to go through stuff really fast. And here's the basic idea. You've already seen, you know, density estimation. We've seen plates, right? And so in density estimation, what you do is you assume that you have some, you know, like parameter theta, and you observe the xi's. And so, you know, if I draw all the xi's independently, that's it. But, well, if that, let's say we take a Gaussian, well, maybe not all data are drawn from the same Gaussian. So what I could do is I could say, well, I first decide which cluster of Gaussians I draw things from, and then I draw the actual observations. And for good measure, I also try to figure something out about the distribution of the parameters. Okay? So that's the graphical model that corresponds to that. Right? And then, of course, I have to adorn them with priors, because I don't know what the means and the variances should be. Likewise, I don't know what my distribution over those discrete events should be, namely, you know, the clusters. And so this is basically a mixture of elements from the exponential family. In this case, Gaussians. So here we basically have two sets of parameters that we need to estimate. Well, the parameters for the Gaussian, and we can use as a conjugate, for instance, a Gauss-Wishart. And the parameters for, you know, this discrete distribution over which of the clusters I'm going to pick. And for that, we can just have a Dirichlet multinomial. So remember the things that we did before, they now come in really handy. Let's write out the joint distribution. So P of x and y. Mind you, I don't observe the y's, but suppose I did. Then the joint distribution would be, P of xi given yi sigma and mu times P of yi given theta. It's a lot of things that you could cluster. Yeah.
Assume that each cluster is a Gaussian distribution.
In this case, I did. But more generally, I could have clusters of multinomials. So for instance, like document models, clusters of Poissons, clusters of anything. So I basically assume that, I pick, let's say, cluster number 42, and then I invoke my generative model for cluster number 42. As a matter of fact, the various generative models don't even have to be the same. I could have a Gaussian for one, and I could have something else for that. As long as things, work out fine, it's okay. So as long as they generate data of the same data type, it's okay.
Give an example of how.
So, for instance, I could cluster documents. Now, a bag of words model is probably less horrible than a Gaussian mixture model, than a Gaussian for documents, because, well, the words come in integer counts. So I could have a multinomial, and that would give me a model which has a multinomial on the documents and a multinomial on the mixture coefficients. So, or you could have a model where you might have some hierarchy over things. So, for instance, maybe I first partition things into English, French, and German, and Chinese, and whatever documents, and then within each of those groups, maybe I cluster by in which period they were written, and then maybe within that period I cluster by topics, or maybe I do some other structure that I could do. But basically, I think that list should already explain that there's a lot of stuff that you could cluster, and people are still writing algorithms for that. But for the sake of simplicity, we're going to stick with the Gauss and discrete. So, in other words, well, we draw the cluster label from the discrete, and we draw the data from a Gaussian given a cluster, and we use the appropriate conjugates, just to make our life easier. The problem is, of course, we don't know the y's, and this is kind of a chicken and egg problem, right? If we knew the parameters, well, we could get the y's really easily, and if we knew the y's, we could get the parameters really easily. And as a matter of fact, this is what Kmeans does. So Kmeans basically actually, first of all, it goes and fixes the variance. And then it says, well, let me assign the data to the cluster that fits it best. And after I've done all these assignments, right, I go for each cluster and compute the new mean. Mind you, I keep the variance fixed. And once I've done this, I go and compute the new assignment, and I keep on iterating between those two stages. This is Kmeans. It's about as simple as it gets for, some clustering algorithm. You can implement it through MapReduce, and at some point people made an industry of that. And they said, well, clustering is solved because we can do MapReduce. As a matter of fact, if you look at what Mahout is doing, they still claim that this is what clustering is all about. Yeah. The problem is, it's a bad model in terms of probabilistic representation. They can get stuck in local minima and lots of other things, so it's actually not a very great algorithm. Any questions? Yeah? Where K is what?
What is K in Kmeans?
So K in Kmeans is the number of clusters, right? So, well, you pick it like so. Or you pick it by saying, well, hey, I would like to have maybe 1,000 groups for my documents, because 1,000 is something that my users can understand. Finding the K itself is a non-trivial question, and people have developed a lot of very beautiful math for that. So for instance, the entire Dirichlet process machinery takes care of this. So there you have a mechanism that automatically adjusts the number of components. You may also want to adjust the relative size of the components, because if I have, let's say, 100 components, I could either say, well, I don't really care about the relative sizes, or maybe they should all be equally balanced, or maybe I want to have a couple of really large ones and a lot of small ones. So these are things that you can impose as a prior. And depending on what you choose, you will get a Dirichlet process. You will, for instance, get a Pitt-Manure process. So Pitt-Manure will give you something where the cluster sizes are more balanced. Dirichlet will give you something where the cluster sizes, you'll have a small number of very large ones and very few small ones. And you overall will have a small number of clusters for Dirichlet. So this is clearly way beyond 701. But look for Dirichlet and Pitt-Manure. People have gone crazy with processes. There is, for instance, the Mondrian process. Then there are something like rose tree processes. This is one of the more bizarre names. There's the Indian buffet process. So whenever you see process attached to something Bayesian, it usually tells you, well, you could potentially get infinite numbers of parameters, and then you can write another 2-3 follow-up papers on how to deal with the mess that you just created. This is maybe a slightly cynical view of things, because they actually address really important problems. So, but it basically is a mechanism for controlling the now possibly infinite complexity that you've created. And so Kmeans, of course, would do something like that. So let's say I have 3 data points, it may partition. Then it goes and updates, and it repartitions